Good evening. Today I'm going to discuss a new topic. This is the Laplace transform or Laplace transformation. Um, to put an end into the previous subject, we dealt with AC in the power system. That was a very interesting topic, very essential to electrical engineers. In that topic, I discussed what is power, different types of power that was introduced, extremely useful technique of analyzing or assessing power within AC systems. So I gave you a lecture and I gave you a homework solution to that. I solved them, I posted them. I hope you all have it. It is absolutely essential that you have it and you study well, preparing yourself for the exam, final exam. So that topic is closed, and prior to that topic was one contact hour I had with you very last time, and that was on frequency response. We went very briefly about the frequency response. And then prior to that, which we did a good job, it was the AC analysis in general, and that was the introduction of phasors, how we analyze AC system, pretty much the same way that the same technique that we analyze the DC system, the complex number. And even prior to that, it was the differential equation, good old differential equation, which is a thing in the past. And we applied analysis, traditional analysis to those second orders, and we solved it. Now we are entering a new technique of analyzing as well as the differential equations, circuits generally. This topic is a kind of a mix of algebra of a complex variable with all those differential equations. So let me introduce here what we are about to do. So the topic is called Laplace transformation. Those analyses were time domain that we did. And then AC frequency domain, which is still a time, but we transformed it into the complex number to facilitate the analysis. This one is going to transform lots of things, including differential equations, circuits, name it, waveforms, time functions, into an algebraic variable, but a complex variable known as the S domain. We will get into that. So title is called Laplace transforming with and the integral that does the transformation. So today's topic will be introducing the basic the function, Laplace function, and the integral, and then we will introduce the transform of very basic functions, like naturally existing functions. And then we will talk about some of the properties of Laplace transformation. It's linear properties, it's superposition properties, etc. And then I will introduce the poles and zeros, which are signifying the complex functions. And then I will go into inverse transform. How do we do a reverse transformation? Using a lookup technique from a table that has already been created. And we will just go over the examples, which I posted that in the lecture note. And in the meantime, I hope all of you have this lecture. You received my email, and you went to Blackboard, under the syllabus tab, look for this heading or title, ECE 2101, Lecture 2. It is a 10-page basically image file that I have sent you. It's a very clear picture. And two of those pages, the two last pages, are essentially copies from the book. It is Laplace properties and the lookup table, but you already have a better version of that in your book. So the 8 pages will be dedicated to the lecture that we have today. Now we're going to start. So let me erase the board. Okay, so let's get started with page 1 of the lecture, page 1 of 10 of the lecture. This is what the Laplace transform is doing. It is called one-sided Laplace transform, f of s, which means it converts functions of time into a special function for time greater than 0 minus to plus infinity. There is a double version of this which we don't use it, basically. Whatever is in the past, we carry it over as an initial condition for the next half, for the positive one, for the right side. So what is the function itself? So this is called the integral, Laplace integral. So simply, if you have a function f of t, we are multiplying it by e to the power st, which is an exponent, and we're integrating between 0 minus to positive infinity. This is, of course, time. Time is the variable, and s is a complex number comprised of a real part and an imaginary part. S can be placed in a plane, which is known as S-plane. S-plane. J omega will be the vertical, and the sigma will be the horizontal axis, so-called the real part of it and imaginary part of that. Now, the outcoming result from this integration, when it is performed on the function f of t, it takes the f of t from time domain and transforms it into f of s s domain with extremely useful properties. So it will take the time function and we will get rid of time function and we'll transform it there. Not only you can transform the f of t, any given function, exponent function, sinusoidal function, name it, step. You can also transform combination, different derivatives. For example, you can transform the f of t by dt into f dash of s. F dash of s is the Laplace transform of the derivative, but in a very useful way when we study the properties. Okay, so this is our transforming function. Technically, how do we shorthand that? We shorthand it this way. We know that it is the integral that does the job, with which say f of s is L Laplace of f of t. So a big L is posted in front of ft. We know that this is going to be the transformed version of ft, which is undergone that integration. You can put, for example, time. F of t equal to t, straight time. Put it t, you've got t times e to the power minus st. You can integrate your t from 0 to infinity. The outcome will be a function of this s. Okay. Let us start step by step. Here, the Fourier transform basically will be identical to the Laplace transform when s is substituted by the j omega. In other words, the sigma part is taken out. So e to the power minus j omega t, f of t, will transform a function of time into a frequency domain. It will be a frequency domain, not s domain. Two are different. And that function will tell you what is the frequency content of a time varying function. Okay, this is set. Now, some Laplace transforms. Let's take a look at it. We will start with the impulse. So we're going to take that integral, and the simplest function, and try to transform it. There you are, 0 minus. So this is our function here, time, f of t. Our f of t is an impulse. Impulse is shown by just an arrow. If 1 unit of arrow is shown, it means it is 1 unit of impulse, delta t. If it was 5 units of delta t, then it will be 5 times delta t. It will be a bigger arrow. So this is our impulse. Just to remind you what is an impulse. Impulse is generally a narrow pulse with a very high amplitude. Theoretically, the amplitude goes infinity, and the width is so narrow, like 0. When you multiply them, 0 times infinity, mathematically, it's not going to mean anything. It's not undecided. But it has one important property, that the integral between minus infinity to plus infinity of delta t, which is the area of that pulse, is 1. This is the definition of the impulse. It satisfies that the area is equal to 1. And that will be 1 unit of impulse. So impulse, delta t, is equal to 0, we can call it, for t other than 0. Surely we can state that mathematically. So everywhere for t, up to the below 0, just below 0, past the 0, it is 0. But when it comes to the time, t equal to 0, right in the origin, its integral has a value of 1. It is a mathematical concept. Okay, let us take a look at the Laplace transform of the delta. Let's see what will come up. So we will stick to this concept, f of t, and the following will emerge. F of s will be equal to, because delta t at t other than 0, the function is 0, so Ls everywhere we will have a 0 multiplying e to the power st here everywhere, except the exact 0. So we're going to evaluate the exponent at time t equal to 0. So at time t equal to 0, this exponent here, e to the power minus st, at t equal to 0 will end up to be 1. So f of s is equal to 0 minus to infinity of f of t. Instead of that chunk here, e to the minus st, we will put 1. This is the value of e to the minus st at exactly t equal to 0. The exact t equal to 0. It is neither minus nor greater. It is exactly at time equal to 0. So e to the minus st becomes 1 dt. And here is the answer. 0 minus to plus infinity, which covers minus infinity to plus infinity. What is the area of f of t, which is replaced by the delta t? Well, this is what we said according to the definition of the impulse. It's 1. So there, you get 1. F of s is 1. So we conclude that number 1, Laplace transform of delta t is 1. Number 1, that shows in the chart. And that will be copied and pasted and saved in the table of the Laplace transform. In the table of Laplace transforms, on one side you will have functions of time. On the other side, you will have a list of f of s, their transforms. So on one side, the beginning, the first one is the delta t. On the other side, it's Laplace transform as 1. So we got that. Next, so we build slowly, go up a little bit. And then we will accept the table. Now, next one is step function. So let me just illustrate something else as well. Now that we're there, the variation here, just to go by the handout. Here, example 1. What will be now the Laplace transform of this impulse here, which is delayed by time t? It doesn't happen at time equal to 0, but it happens at t delta t. So how is it going to show up in the integration? Okay, let's look at the, again, definition. The function, we erase this and we post delta t. Here, you have a delta t sitting there and you wanted to integrate to get its Laplace transform. The function delta t is, we should call it actually delta t minus t, to be correct here. T minus t, this function. The function delta t minus t mathematically implies that the delta t minus t is 0 all over the places, except at the time t, which we don't know what the value is. But we know that the integral of delta t minus t from minus infinity all the way to plus infinity, which includes the 0 minus to this side, integral of that is equal to 1. So go to the function and check it. So this is going to be 0 most of the time. Most of the time it is 0. Let's check the time that it is not 0. What is the value of e to the st? So you need to substitute here for t equal to t into the exponent. So your exponent will become e to the power minus t s. This will be the value of the exponent. Now, this is not a function of the time, it is a constant. So f of s is going to bring this out, e to the power minus ts. Now apply integration to the delta t minus t dt. Okay, and we know what that is. Delta t minus t is the area under the impulse from minus infinity to plus infinity, that's the range, which means it's going to be 1. 1. So what is the outcome? Outcome is f of s is equal to e to the power minus st. That's it. We get the function for the delayed impulse. So you can say Laplace transform of delta of t minus t is simply e to the minus ts. That's it. So if you see an impulse which has a Laplace of 1, what about if the impulse is delayed? You simply multiply by e to the minus ts. Actually, this is a very helpful concept. Every function that is shifted in time, every function that is completely shifted in time by a t, its Laplace will be the Laplace when it is not shifted, multiplied by the e to the power minus ts, which is called the shift theorem, one of the properties, which we will look at that later. So this explains how you will account for the Laplace. So far we have Laplace of that delta is just 1. Laplace of delta that is shifted by an amount of t is e to the power minus st times 1. Proportionality. Proportionality theory says Laplace of 5 delta t will be 5. Laplace of 5, for example, delta t minus t will be 5 times. Just like a scalar, it will multiply. Now, let us look at some real function, something that has a physical meaning, and that is the step function. These are the simplest functions. So we're going to look into the step function. Step function is shown by this profile versus time. This is f of t. It's called ut with unit step. It's 1. Otherwise, it's 0. Mathematical description will be u of t is equal to 1 for t greater or equal to 0, and u of t is equal to 0 for t less than 0. So here we are going to post ut. Okay. 0 minus. So we are going to post u of t. So how are we going to take that integration? Very simple, actually. Look at the limits of integration. We are taking it from practically 0 all the way to positive infinity. Although it is minus 0, but in practical sense, it doesn't contribute anything. So let us integrate it. For u of t, we need to substitute just 1. It becomes 1. So f of s becomes 0 minus to the infinity of just e to the st. That's simple. This is integral of exponents, which is equal to 1 upon minus s. Sorry, 1 upon minus s e to the power minus st, and you will put the limits 0 minus and infinity. So you'll get minus 1 upon s. That one will be e to the power minus infinity, e to the st, when t is infinity, e to the minus infinity, minus, you will substitute e to the power 0 or minus 0, it doesn't matter. Okay, so this will converge to 0, it's e to the minus infinity. This will converge into 1. So you will have minus 1 upon s times minus 1. 1 over s, period. Okay, we got it. In the table, one more function is added. The function is Laplace transform of ut straight 1 over s. Okay. What will happen if you apply a function that is a step function that is delayed, say by amount of t, such as 0, then you apply the function 1 by an amount of t. Okay. Description. Description would be, for the green function, delayed function, u of t minus t would be, it is equal to 1 for t greater or equal to t. Otherwise, u of t minus t will be equal to 0 for t less than t. In other words, this portion is 0, that portion is 1. Okay, let us plug it into the equation and see what will come out with regard to that mathematical fact. Okay, so we're going to erase this and substitute it with u of t minus t. U of t minus t, the delayed step function. Okay, let's take the integration. When you're integrating that function, you notice that u of t minus t is 0 before t. So it's useless that I start from the 0. I'm better off to start it from t, that time, because below that time, before that time, the function is 0 here. Doesn't have any height. Then integral of u of t. Now we're looking at what time interval? T to positive infinity, which means value is 1. So I'm going to post 1. Then I will plug in my transformer, e to the power minus st dt. By the same token, we will just integrate this. It will be minus 1 upon s, that's like e to the power alpha x, minus alpha x. Its integral is 1 over minus alpha e to the minus alpha x. And then e to the power minus st, put the limits at t, and we put there an infinity for the uppercase. Work this out. Minus 1 upon s is equal to, first top, minus infinity, then the bottom, e to the power minus t s. Close it. This part will go to 0, e to the minus infinity. That part will stay as minus e to the power minus ts. The total outcome will be equal to e to the power minus ts over s. There you are. So this will be the or the transform of the Laplace of u of t minus p equal to that. Okay. Let us compare that against the transform of u of t, which came to be 1 over s. So what's the difference between the two functions? Same height, same everything, same description, except this one starts at t equal to 0, it's 1 over s. This one that starts at t is multiplied by e to the power minus ts. Bottom line is, every time that you have a function that is shifted, you don't have to operate an integral on it. Consider the function in the origin, the f of t, get its Laplace, which was 1 over s. And when you see a function of time that is shifted, you will simply multiply the function by e to the power minus ts to account for the shifting in the time domain. So every time you multiply by e to the power minus ts, some kind of exponent with a complex number at the top of it, with the time t, it's called delay function. When you multiply by that, you multiply e to the minus t by 1 over s, it implies that it is shifted in time. For example, suppose you have a train of impulses, delta t minus t, delta t minus 2t, minus 3t, etc., etc., a train of impulses. What could be that? It could be, in time domain, a constant that you have been sampling here with an impulse, then another sample you're taking with the time of t, another 2t, see equal intervals here. What would be the Laplace transform of this series? You know, the total function, which is made from delta t added to delta t minus t, delta t minus 2t, etc., etc. What will be the Laplace transform of that, of this whole thing? This is how to do it. Your f of s will be equal to delta t would be 1. Delta t minus t would be 1 times e to the power minus ts. Delta t minus 2 would be 1, that's the Laplace of delta 1, multiplied by e to the power minus 2ts. If there were more and more and more samples, it would go 1 e to the minus ts, minus 2ts, minus 3ts, minus 4ts, etc., etc. It will just give you a whole lot, which will be kind of, formations here. Formation of a S-domain presentation of impulse waveforms, samples, but in the S-domain. So you will remember this when you come to Z transformation. Very soon you will see ahead of yourself. So in the Z transformation, I don't want to go ahead, but again, this will be transformed. F of s will be further transformed into Z transform by substituting e to the power minus s ts by a z to the minus 1. In other words, z will be e to the power ts. So you will get a series 1, z to the minus 1, z to the minus 2, z to the minus 3. The series will have a convergence. You will add them up, you'll get a function, and then you'll get z transfer functions, and so on. So foundation of what comes next will be built on the Laplace transform you're learning today. Okay, so let me just bring you back what we did so far. I introduced what the function is. I introduced what the delta is, got the transform of the delta, which is Laplace of that is 1. Then I introduced two cases, delta that was shifted, step and step that was shifted. We noticed that and e to the minus st is multiplying here. E to the minus st is multiplying. This is it accounts for time shifting in the time domain. So you take the same old Laplace 1 over s of the step, and you simply multiply by e to the minus ts. That means the Laplace transform of the time function we had it shifted in time domain. Right. In this fashion, let me tell you, you can create lots of things. You can have multiple steps like that. So these are the steps that are delayed and added, each with a different amount, different height. You can Laplace transform each one and use e to the minus st to describe that staircase function in Laplace domain. It can be done. So it is a very powerful, tell you what, it's a very powerful technique. Okay, so let me erase this. Now we're going to look into.
Professor?
Yes, go ahead.
Sorry, just one question. Would it be any meaningful for any function to be shifted to the left?
Yes, it will be. For example, when you are sampling something, you see you have a waveform. For example, you have a, let me get rid of color. A lot of meaning into that. Say you have a time domain function. You have, for example, a sine wave, let's say. So you're sampling it, you're producing impulses proportional to the height of that waveform. Okay? And you want to come up with a function that will describe the impulses, the train of impulses. And we can do that. This will be delay functions. And if those delay functions are further transformed with a z equal to e to the power st, if we make such a substitution, where t is the interval and is known as the sampling interval that you're taking with z, you will get an entirely function of z, which is known as the z transforms of sine wave, z transforms of step, z transforms of etc. It will allow you to do some important analysis, this z transformation. But the foundation of z transformation is Laplace transformation. So z transform is the transform of the Laplace transform, especially the transform of the impulses weighed at the values of the function itself, time domain function. Great application there. You will see a lot more, not in this course, but later when you emphasize on the sampling.
Sorry, I'm still not quite getting it. I mean, since the integral have the lower bound at 0, will we ever shift any function to the left?
There are double-sided versions of the Laplace transform, but the common one that we will use for circuit analysis, because after knowing an initial condition, we are not interested in the past, what was in the past. So we normally apply this integral, which is called single-sided Laplace transform. This is the one that you have the tables on. So that's the simple version of it, the right side of the integral. So single-sided, we're using the right side of the integral. Okay?
Thank you very much.
You're welcome. So let us now, I just showed you on page 2, just how Laplace of step was 1 over s, Laplace of delayed is e to the minus ts over s. If it was delayed, you had a multiple of steps, like this one, staircase, which is a step, and then another step adds, another step adds together, and you wanted to show that waveform in the Laplace domain, you simply take 1 over s for the first step, and then for the next would be 1 over s e to the minus ts, 1 over s e to the power minus 2ts, if they were equally spaced from each other, and then you can construct the wave shape. Now, let me define. Because you saw a function is emerging, finally, f of s. For a function of time, this function may have, it's a rational function, and it has two parts, a numerator and a denominator. It will be, the numerator will be a polynomial in general. Denominator will be also a polynomial. Here is the special case. E to the minus ts is not a polynomial, and really there's no other way of showing it as a polynomial. But look at the step. The step is 1 over s part. Simple step. Of course, it's a rational function. The numerator polynomial is 1. The denominator polynomial starts with the power s to the 1. It's just s. Just a single variable. Let me just illustrate the rest. General form of f of s. So if we had continued with the function, we can get different functions of time, which maybe I will show you. Yes, I showed you one more of that. These functions generally will be rational functions of s, d of s. N of s will be a polynomial. A polynomial, and this will be a polynomial. In a practical system, the highest power of the polynomial will be less than the denominator in physical and practical system. So you will probably never see an s with a higher degree than the denominator. It's either equal or it is less. For example, if the denominator is s cubed and s squared, etc., the numerator will be the most s cubed plus that, or s squared plus. That's the highest power. The highest power of the numerator in a practical system is always less than the denominator. The reason is if the highest power of the numerator, even if it is equal to that, theoretically that system has an infinite bandwidth, frequency bandwidth, which no system has infinite bandwidth. But when it is less, then the system has a limited frequency bandwidth, and everything it has a limited frequency bandwidth. So, important thing, function f of s, the Laplace, comes as a rational function, polynomial, numerator polynomial, denominator polynomial. Next. These polynomials, for simplicity, may have, if you set n of s equal to 0, you will get a set of roots. Values of s here. Typically n of s, let's say n of s is equal to s plus z1, s plus z2, multiplied multiple parentheses. Okay. The values of s that make the function 0, therefore it makes the numerator equal to 0, are called the zeros of the function. So for s equal to z1 minus z1 minus z2 minus z3, etc., f of s is equal to 0 because n of s is equal to 0. So values of s that make the function 0 are called the zeros. Opposite of that. P. Excuse me, not P, D. Denominator. D of s equal to 0. D of s, again, can be s plus p1, s plus p2, etc., etc. Multiples of parentheses. To be complete, and we will see, sometimes we get complex poles, but the complex poles will appear in conjugates. For example, you may have a situation where there will be an s plus alpha plus j omega O, and another one, s plus alpha minus j omega O, and so on. They could exist within all of these poles. And when you multiply these two together, you'll get a quadratic, which is with all real coefficients. So you may have a quadratic with all real coefficients, but if you break it down, it will give you complex numbers. Now, these values of s, minus p1, minus p2, here, minus alpha plus j omega O, minus alpha minus j omega O, and so on. These values, if they are substituted back into the function, we are going to make the denominator 0 because those are the roots of the ds. So poles are the roots of ds. It will make the function infinity. So it will make f of s equal to infinity for all values of the poles. So by definition, a pole is a value of s that makes the function infinity by making the denominator equal to 0 in plane. A function, therefore, may have poles and zeros because it may have all shapes. The poles and zeros are shown in a diagram. This is an example of a pole zero presentation of the function. So let me erase this. You have it right there. Here, we have a function n of s equal to, it has s plus 1, s plus 2, then it has s plus 1 plus 2j, s plus 1 minus 2j, and they always appear in conjugates, which means they were the outcome of a second order like that, 2s plus 5. Here, you can't break it into two real numbers, you know. The delta under the radical is a negative, so it results into the complex. So say that, and then you have in the denominator, I showed you with the red color as s plus 3, s plus, let's say, 4, and then you have s squared, 4s plus 5, which this breaks down into s plus 2 plus j, s plus 2 minus j. Okay. So this is the breakdown, so-called solution of that second order. How do we present? How do you present your function in the S-plane. This is the presentation. You go to the S-plane, sigma j omega, it's called the S-plane, and you present it in this system, which is known as the pole zero diagram of Fs. If you give me the pole zero diagram of a function, I can create the function for you. Very simple. The numbers there can be put back into the parentheses. For the zeros, I'll put zeros. For the poles, I'll put the poles, and I will create the function for you. Pole zero diagram of a function. So that is the jargon for f of s. You will hear millions of times in the control engineering class. Okay, let us show the picture now. Simply, it is simply plotting those values. Let us plot the poles. I think I put something else there. Oh yeah. Here I had another S, which I missed. Here, S. So what is the pole corresponding to S? Put S equal to 0, S equal to 0. So S equal to 0 is a pole. S equal to -3 is a pole. S equal to -4 is a pole. They call it P, SP, SP1, SP2, etc. So here is presentation. SP equal to 0. Poles are shown with an X. If they are single with one X, sometimes if they are double, two X's are put together, looks like an asterisk, but you have to write double because we don't know if it was triple what it would be. You have to write triple. And then -4, -3, so this is 2, that is 1 -2, -3 here, and then you get 1 at -4, -3 and at -4. And then you mark the complex one. The complex ones have a complex component. So it will be -2, -j, and -2 plus j. 2 is here, and j. So it will appear right here. That's j, and this is a -2. So the axis that you see is presenting poles of f of s. The zeros. Zeros will be shown with a empty circle. So you have to plot them. S plus 1. The zero of that will be -1. Equated to 0, s equal to -2. And so on. So 0 should be at -1. Then at -2, here, there's a 0 there. And we have another complex 0, -1 plus 2j, -1 plus here, 2j, and that's a -1 real part. And another one, which is the image down there, symmetric. This is the -2j, the mirror image. Always without exception. Complex poles and zeros, they appear symmetrical, which makes them conjugate. It can't be otherwise. You cannot have a single pole without. There's no real system that has one single imaginary pole or zero. They always come in pairs, conjugate. This is it. Pole zero diagram. Pole zero diagram. And you will hear this, as I said, a million times when you go to the control engineering class. So you better know where the instructor is referring to. It's a function, general, a rational function, numerator, denominator. The roots of numerator are called zeros. The roots of denominator are called poles. Poles are characterizing a lot about the system. Okay. Now, let us take a look at the Laplace transform of an exponential function. This function will show you really that it has a pole. The simplest of all. Okay. So what we have here is Laplace transform of f of t equal to e to the power minus at ut. Okay. What type of a function is that? This is the exponential function decaying. If a is positive, it will decay. If a is negative itself, it will grow exponentially. U of t is basically the step function which is associated with it. We know that definition of u of t. U of t is 0 for time less than 0. So this function, therefore, does not exist. F of t is 0 in the past. The one that you question, what about from minus infinity to minus 0? We have to put a kind of a start to everything. Everything starts from certain thing. So that is why it is masked with u of t. Okay, let us integrate that and see what will happen. Here is the Laplace function. E to the power minus at. For u of t, in that interval, I'm going to account 1. So I'm not even writing it here. E to the power minus st dt. There it is. So why u of t doesn't show? Because look at the interval, it's greater than 0. So it's a 1. Why should I write 1 here? Now, how does the function look like in time domain? Okay, this is what it is. This is time, here is f of t, and this is what you have. It's 0, and then exponentially it decays. Okay. This is the e to the power minus a of t. Most exponential RC discharges, they have that time constant. You can say a is 1 upon tau, the time constant. Okay, integration. If you integrate that, f of s will be equal to, you can combine minus, this will be a plus s of t dt between 0 to infinity. So if we integrate that, it will be 1 over minus s plus a multiplied by e to the power. First you put here e to the power minus a plus s, and you put infinity. Yes, infinity, and here you put 0. E to the power of a t, of course, t. If you put the infinity there, e to the power minus infinity will bring it to 0, and then you put t equal to 0. This will be e to the power 0, which will convert that into a minus 1. This will drop to 0, that term. It will vanish. This term will become minus 1. Bottom line, Laplace transform of e to the power minus at u of t will become 1 over s plus a. Now you have a rational function. This function has only one single pole. Show it. S plane, sigma, and the j omega. It's here. minus a. S plus a equal to 0, s is equal to minus a. If a happens to be a positive number, please note, if a is positive, look at the equation. If e to the power minus at, a is positive, do you notice that the function is decaying against the time? Because it's a decaying function. What if a is negative? A is negative. So the function will be e to the power minus at if a happens to be itself negative. Then this function would be actually growing exponentially, because negative of negative is a positive. You get positive t. And look what will happen if a happens to be a negative. A negative will project it here. This is when a is negative. So we can associate one thing. This is very crude, but it gives you a good idea. Gentlemen, in a transfer function, when a pole, only pole, not the zero, a pole happens in the left-hand plane, because this is the positive, it makes it, pole becomes negative. If negative side poles exist, that system is going to decay. It's going to die down to 0. It is said to be stable. If a pole falls to the right side, for example, you have s minus 2. You solve that, s will be equal to 2. 2 will be here. But if it was plus 2, it would be minus 2 on this side. Here, with that, your solution is 2t, positive 2t. And that means exponential growth against the time. That system is unstable. That is why we get the pole diagram. The S-plane presentation comes handy in a quick glance of whether a function is, there is a time function in the fs that is growing out of control, increasing with a positive exponent here, or it is a decay. You know, you apply a step, it eventually decays. Or you apply a step, it responds to the step after some kind of oscillation. If it shows signs of decay, the poles will be in the left-hand plane. If it shows a signs of, you apply a step, it goes like this, increasing in amplitude, then the poles will be in the right-hand plane. So this is a prelude to control engineering. That is why it needs to be brought up at this point. Okay, so we got the functions of exponential function, and very simple. We got the Laplace transform of that. Are there more functions? Yes, there are a set of handful of classic time functions, and we have a table for that. Okay. We have a table. We will go there and we will look at it in the end. Okay, let's take a look at the Laplace transform of a composite function. Now, this is one of the properties. Laplace transform of two functions, f1 of t, combined with f2 of t. I'll put them in brackets. Highlighted more. So what will be the Laplace transform of, say, two independent functions, but they're superimposed on each other? This is the superposition. It will be f1 of s. All you have to do is to take Laplace of one, add to the Laplace of the second. That's it. So they can be treated individually. If you have a mix of functions, say I have an exponent, I have another one with different time constant, what is the Laplace transform? So this theory is one of the important ones. You know, it's superposition basically, a linear combination of functions. Or if you have f1 of t plus 5 times f2 of t, what would be the Laplace? Okay, go get Laplace of f1, get Laplace of f2, multiply by 5. So post the 5. So 5 times of f2 of s could be something like that, adding to the first one. Pretty easy to remember. Now, look at this example. Here, example 2. It says, find the Laplace transform of 2 times e to the power minus t added to 3 times e to the power minus 2t. So we have two functions here. One is f1, 2f1. The other one is 3 times f2. Look at A. A is 1 in here. A is 2 in there. They are both decaying. This decays faster. This decays slower because that time constant is smaller than this time constant. Time constant is reciprocal of A, generally speaking. Remember e to the power minus t over rc, recall that? This is e to the power minus 1 upon rc t. So 1 upon rc is the A they're talking about. If A is large, it means you have a small time constant, the RC product, or L over R product, if you have inductor resistance. If A is small, then you have a large time constant. It's a very slow decaying function. It will become natural slowly. Okay, so we want to determine the overall Laplace transform and present it as 1. How do you do that? Okay. Deal with them independently. So this is 2 times Laplace transform of e to the power minus t. And then 3 times Laplace transform of e to the power minus 2t. Okay, there. Go to the table. This is our short table. Here, A is 1, there A is 2. So the outcome of that will be 2 over s plus 1. This one will be 3 over s plus 2. Take a common denominator. You will get s plus 1, s plus 2. And then you will have here 5 times of s plus 1.4. There it is, classic function. Tell us what is the pole zero diagram of that function very quickly. Sigma and j omega. Pole zero diagram of f of s. Look for poles. There's a pole at -1 at -2. This is -1 at -2. Denominator. There is a 0 at 1.4. -1.4. So this is where the 0 is. How do I separate one from the other? Poles are always marked with X. Zeros are marked with a circle, kind of an empty circle. That's it. This is the pole 0. And you just saw the evidence of this function existing. And you saw the evidence of numerator polynomial, which is a simple first order. Denominator polynomial, which is a second order. If you multiply and combine them, it will be s squared 3s plus 2. And there we are. That's the start of the application of Laplace transform. So this was the page 3 of the lecture notes. Then we're going to get into real problem solving. Okay, now, do you have any question, please ask? Now, I have given you here 3 scenarios. Let me keep track of my time. Actually, we start at 7, it's 8:10 already. Yeah, let me just lay this down on the board, and then we will take a break. I will tell you. We'll take some 5 to 7 minutes break. In a minute. The examples that will follow will help you to solve your homework problem and conclude chapter 14. So today, I'm doing this really, really fast, and it will conclude actually chapter 14. All right, before I start the case-by-case study, let me bring your attention to the table. I showed you a table. There are 2 of them actually. Where is that? Hold on a second. It can't be. It can't go very far. Let's see. Let me find the copy that I sent to you. Where is that? Gee. 9 of 10. Where's the 10 of 10? 6, 7, 4, 9 of 10. This is unbelievable. Paper right in my hand has disappeared. It's the 10 of 10, which is a reference. You have it in your book. Page 10 of 10. Transform table. There's a list of functions there, which the transform is shown right in front of you. That's amazing. I cannot find the very simple paper which is supposed to be in the pack. I know where to go. Maybe here. No. Okay. So I'm forced to show you the book, which I didn't want to. Okay. All right. This is the book. Page 892. Page 892. There is a list of various types of functions of time and the transforms. It starts with the delta t. Here, I will write a few of them. Delta t, this is the time domain, and this is the s domain. So delta t is 1, which I showed you. U of t turns to be 1 upon s, and then it keeps building. E to the power minus at ut is 1 over s plus a. I will list only a few ones. T times u of t. So this is a ramp, ramp that goes like this against the time. That is 1 upon s squared. And then you have t times e to the power minus at ut. This is the exponent multiplied with the ramp, which is 1 over s should be plus a squared. When you see a square term, the pole is a, of course, pole is s equal to minus a, but it is a double one because the power is 2. You've got it twice. This happens when the delta under the radical, you have a second order, the delta becomes 0. So it gives you duplicate form. And then you have a generally t to the power n e to the power minus at would be 1 upon s plus a to the power n plus 1. So if you have a multiplicity of roots, poles, like n plus 1 poles, then the time function pertaining to that would be t to the power n. For example, if n was equal to 3, if this was a parenthesis to the power 3, this would be to the power 2. You would have a t squared times e to the power minus 8. And t to the power n minus 1 over n minus 1 factorial, n minus 1 factorial, if you had a function of time to the power n minus 1, e to the power at, the answer to that would be equal to 1 over s plus a to the power of n. It will go 1 over s plus a to the power n. So in this manner, we will get a different function. One important one, if you notice, they are all real. The poles are real, sometimes multiple. The one which is significant is the complex. I want to show that, and we'll take a quick break. This is the complex. If you have e to the power minus at sine of omega t, this is a sinusoidal decaying waveform. The Laplace transform of that would be here. It would be omega over s plus a squared plus omega squared. We need to be expert on that one. So that transforms into that function. If you have e to the power minus at cos omega t, the transform would be s plus a over s plus a squared omega squared. A couple of homework problem is emphasizing that, which we will go over. So these are the set of the most important functions and their transforms, which you should get used to it when it comes to problem solving. Okay, then let's take a break, and then we will be back in 10 minutes, shall we say? Let me time it. Yeah, 10 minutes. So 10 minutes break. Starting